Welcome to the Explainer. Today, we're doing something a little different. We're going to perform a digital autopsy. Yep, we're cracking open the brain of your computer, the CPU, to figure out how it actually thinks, acts, and executes every command you give it.
So, here's what's on the slab. First, we'll identify the core organs, what makes it tick. Then, we'll trace the information superhighways, the neural pathways, if you will. We're even going to watch a single thought happen in real time. And to wrap it all up, we'll look at the two main blueprints that architects use to design these digital brains. Let's get started. All right, first things first, let's dive right into the core components. If you want to understand how a CPU works, you have to know about the three key players running the whole show. Okay, so first up is the absolute star of the show, the processor itself, the CPU. Seriously, think of this thing as the central command for your entire computer. Every single thing you do, every click, every key you press, it all gets broken down into instructions, and it's the CPU's job to execute them. Without it, nothing happens.
Now, deep inside that processor, you'll find what's called the ALU, or the Arithmetic and Logic Unit. The easiest way to think about this, it's the CPU's own ridiculously fast calculator. It crunches all the numbers, addition, subtraction, all that good stuff, but it also handles logic, like, is this number bigger than that one? All that happens here.
And then you've got the control unit, or CU. Now what's interesting is the CU doesn't do any of the math itself. Instead, it's like the conductor of an orchestra. It takes in instructions, figures out what they mean, and then tells every other component what to do and exactly when to do it. It's the ultimate manager, coordinating that whole flow of data. So if you remember one thing from this section, make it this. The ALU is the doer, right? It's the muscle doing all the heavy lifting. But the control unit is the director, the brain behind the operation, making sure everything happens smoothly. They're a perfect team. Okay, but for all this to happen at mind-bending speeds, the CPU has a problem. It can't just sit around waiting for data to come from the computer's main memory. That's way too slow. So it needs its own super-fast personal notepads. And these are called registers. So what are registers? Well, they're these tiny, incredibly fast little bits of memory located right on the CPU chip itself. The best analogy I've heard is a chef's mise en place, all the little bowls with prepped ingredients. Registers hold the exact data the CPU needs right at that very second for whatever it's working on. And what's really cool is how specialized these things are. I mean, look at this table. Don't worry, you don't have to memorize this. Just appreciate how each one has a very specific job. You've got the program counter, which is basically a bookmark, keeping track of the next instruction. The accumulator, that's where the results of calculations are stored. Each one has a role, and this incredible division of labor is what makes the CPU so dang efficient. Okay, so we've got all these different parts, the ALU, the control unit, all those specialized registers. The big question is, how do they all talk to each other? How does information get from one place to another? Well, the answer is a system of electrical highways that we call buses. And this information superhighway has, you guessed it, three main lanes. You've got the data bus, that's what carries the actual data, the what. Then there's the address bus, which says where that data needs to go. And finally, the control bus acts like the highway's traffic signal system, sending out timing signals to make sure nothing crashes. It's a pretty elegant system. All right, we know the anatomy now, so let's put it all together. Let's actually watch the CPU have a single thought. This all happens through a constant, never-ending loop called the Fetch-Decode-Execute Cycle. This little three-step dance, fetch, decode, execute, this is literally the heartbeat of the processor. I mean, everything your computer does, whether it's moving your mouse or rendering a blockbuster movie, is just this one cycle repeated billions and billions of times. So first up, fetch. The CPU looks at its bookmark, remember the program counter, to see where the next instruction lives in memory. It grabs that instruction, and here's the really important part. It immediately moves its bookmark to the next instruction. It's always thinking one step ahead. Next up is decode. This is where the control unit steps in. It takes that instruction it just fetched and basically reads it. It breaks it down into two simple parts. What's the command, like add or move, and what's the data that I need to do it with? And finally, execute. The instruction gets carried out. If it's math, the ALU jumps in. If it's moving data, another part takes over. And the second it's done, boom! The whole cycle starts right back over again, billions of times, every single second. Okay, so we know the CPU's basic move is that fetch, decode, execute cycle. But what makes one CPU so much faster than another? Why is the latest chip better than one from 5 years ago? Well, it pretty much boils down to 3 key performance factors.
And those 3 factors are clock speed, the number of cores, and cache memory. Think of it like this. Clock speed is how fast it can think. Cores are how many things it can think about at the same time. And cache is how fast it can grab the info it needs to think. Let's look at each one.
First up, clock speed. You always hear numbers like 3.5 gigahertz. What does that actually mean? It means the processor's internal clock is ticking 3.5 times billion times a second. And each one of those ticks helps push the Fetch-Decode-Execute cycle forward. So yeah, a higher number here means a faster heartbeat and a CPU that can just blaze through instructions.
Then we have cores. This one's pretty intuitive. Having more cores is literally like having multiple brains inside one chip. Each core can run its own Fetch-Decode-Execute cycle completely independently. That's why having, say, an 8-core processor is so amazing for multitasking. You can do a bunch of things at once without slowing down.
And last but not least, cache memory. This is so important. Think of the cache as a tiny, super-fast library right next to the CPU. Instead of having to make the long, slow trip to the main memory, the big city library, to get data, it can just grab what it needs from its own personal bookshelf. And you can see there are different levels, with L1 being the smallest and fastest. This whole system is designed to stop the CPU from ever having to wait for data. It's all about eliminating bottlenecks. All right, for our final section, let's zoom out a bit. We've seen the components, but how are they all actually laid out? What's the overall blueprint for a digital brain? Well, it turns out there are 2 major competing designs. So you've got 2 classic blueprints. First, there's von Neumann. This one is simple and elegant. It uses one shared memory for both instructions and data. Think of it like a library with only one door. It's simple, but it can get crowded. Then you have the Harvard architecture. This one is all about speed. It gives instructions and data their own separate memories, like a library with 2 doors. This is a game changer because it means the CPU can be grabbing the next instruction at the same time it's working with data. It's way faster.
So you're probably wondering, which one do we use today? And the answer, which is just brilliant, is both. Modern processors use a hybrid approach. For talking to the big main system memory, they use the simple von Neumann style. But inside the CPU itself, for that super fast cache we talked about, they switch to the Harvard model and split it up. It's genius, really. You get the best of both worlds, simplicity for the overall system and raw speed where it matters most.
And that brings us to the end of our digital autopsy. We've seen the intricate, clockwork-like design of a modern CPU, all the way down to how it cleverly mixes and matches architectural blueprints for maximum performance. Which leaves us with a really big question. Where do we go from here? As we demand more and more power, what do you think the next evolution of the computer's brain is going to look like?